end of the previous lecture we were discussing about two important terminologies, the spectral radius of convergence and the rate of convergence, and we will be continuing with that. So, let us try to focus a bit on first the spectral radius of convergence. So, as we have seen that if you want to have a very few number of iterations to satisfy convergence, then what should be the spectral radius of convergence. So, just keep in mind that essentially the rate of convergence is related to log of 1 by the spectral radius of convergence. So, if you make a plot of log x versus x, so it will be something like this, right. Now that means if x is 1 by rho, as you have smaller and smaller values of rho, remember that we have the maximum value of rho as 1 to achieve the sufficient condition for convergence. So, that means it is a positive fraction. So, 1 by the positive fraction is a number which is greater than 1. So, smaller the value of rho, larger is this value of x which is say 1 by rho, and larger is log x, right. So, essentially you are dealing with variations towards the right side of x equal to 1 because rho is less than 1. So, as you increase x, your log x increases, and in the limiting case when rho is very small, then log x is very large. That means the rate of convergence is very large. Theoretically, when rho tends to 0, x tends to infinity, so log x also tends to a very large number, and when log x tends to a very large number, that means the rate of convergence is very large. So, you require a very few number of steps to achieve convergence. So, what we can infer from this? We can infer from this is that smaller you keep the spectral radius of convergence, better it is in terms of the rate of convergence. So, to achieve a high rate of convergence, your spectral radius of convergence should be as small as possible. That is the first and foremost thing that we can infer. Now, but how to assess what is the spectral radius of convergence? There are several ways in which you can assess the spectral radius of convergence, but we have to keep in mind is that again to do that in a straightforward way, we need to calculate the eigenvalues of the matrix M, and eigenvalue computation is also expensive. Just like we had seen that the power computation of the matrix M, it is expensive. To get rid of that problem, we came down to the equivalent eigenvalue representation, but equivalent eigenvalue representation, if you want to use that, you need to calculate the eigenvalues of M, that is also expensive. So, we need to go to something which is again equivalent to the eigenvalue representation, but something which is computationally much more straightforward. To do that, we will consider the norm of the matrix M. So, remember that MV is equal to lambda V. Lambda is the eigenvalue of the matrix M. Now, we know that norm of MV is less than equal to norm of M into norm of V, and because MV is equal to lambda V, Therefore, norm of MV is mod of lambda into norm of V, right, and from these two it follows that mod of lambda less than equal to norm of M. Since mod of lambda is less than equal to norm of M, maximum of mod of lambda is also less than norm of M, that is the spectral radius of convergence is less than equal to norm of M. So, if you can have an estimate of the norm of M, then that is good enough to give you a bound of the spectral radius of convergence, and that can in effect be substituted in place of the eigenvalue representation to get an estimate of the characteristics of convergence. Okay. Now, when you say the norm of M, again the question comes that which norm? I mean there we have seen that there can be several types of norms possible. So, but some of the limiting norms are, and some of the norms which are easy to calculate are the first norm and the infinity norm, that is the column sum norm and the row sum norm. So, a conservative estimate, so an estimate of rho is given by the maximum of the row sum norm and the column sum norm. That is, out of these two types of norms, whatever norm is the maximum one, remember that you have to keep the maximum of the maximum of the lambda, mod lambda maximum out of all lambda i's, that you need to keep less than 1, and norm of M is always greater than that one. Out of all possible norms of M, whatever is the maximum, that if you keep less than 1, that means you are maintaining the, or you are satisfying the sufficient condition for convergence. So, you are becoming very conservative. You know that whatever is the norm of M, that is greater than rho. For you it was sufficient to satisfy rho less than equal to 1, but if you satisfy norm of M less than equal to 1, then implicitly you are satisfying rho less than 1 definitely, and out of the two extreme norms, one of those whatever is the greater one, that you satisfy as less than 1. So, that means the other one will automatically be less than 1. So, your sufficient condition for convergence boils down to less than or equal to 1. Now, let us take an example and see that what can be the norm for the methods that we have learned so far. We will take an example of the Jacobi's method. Why we take the example of the Jacobi's method? Again, for estimating the rate of convergence or any convergence criteria, Jacobi's method will give you a conservative estimate, because Gauss Seidel is faster than the Jacobi's method. So, if it works for Jacobi in an efficient way, you expect that for Gauss Seidel it will work in a more efficient way. Now, for the Jacobi's method, what was M? Minus D inverse L plus U. This was M for the Jacobi's method. Where let us again write what are the entries of L, D and U. So, D is A11, A22. See, eventually the matrix M is a derived matrix. The original matrix which was given to us was the coefficient matrix. Therefore, we should be able to write everything in terms of the entries of the coefficient matrix. So, this is the D and L is A21, A31, A32, then AN1, AN2 in this way. This is L and U is A23, A24 in this way, sorry, I will start with A12, A13 in this way, A1n, then A23, A24 in this way, A2n and so on. Now, D inverse into L plus U. So, D inverse roughly represents what? It remember the diagonal for each row contains only one number. So, D inverse roughly represents the division by the diagonal component of the matrix. For a single scalar number, inverse is 1 by that one. For a matrix where you have more number of entries, it is systematically calculated in a more general way, but the diagonal matrix is a special type of matrix where only diagonal term is there. So, you can write this as L plus U means sum of the off diagonal terms divided by the diagonal term. So, now if you want to calculate the norm of this one, you can calculate either the column sum norm or the row sum norm. Let us consider the row sum norm as an example. So, if you consider the row sum norm, then what will be that? So, sometimes out of the row sum and the column sum norm, the row sum norm is used as a criterion. I mean, there is nothing hard and fast about it, one could use column sum or the max of those two, but usually any one of those is considered. This is just a matter of convention, there is nothing very fundamental about it. It is just a convention that in many cases the row sum norm is used as a representation of the norm of the matrix. So, what will be the row sum norm? For any row we divide by the corresponding diagonal. So, AII for the ith row is the diagonal. So, you divide it by this one, so mod of that one. In the numerator you have summation of mod of Aij where j is not equal to I. And this you expect to be less than equal to 1. To satisfy sufficient condition for convergence. Now, try to relate this with the CFD discretization. in CFD discretization, using the nomenclature that we have considered for the grid layout, this is summation of A n b, that is neighboring A's, divided by summation of AP, mod of both. So, the diagonal represents the grid point P, and the other ones represent, the off diagonal ones represent the neighbors. So, this is like the point P, wherein the other sides of it you have the effect of its neighbors. For a one dimensional system it is a tridiagonal matrix, whereas for a multi-dimensional system it is for a two dimensional system, considering the finite grid considering the finite volume grid layout that we had considered, it is a pentadiagonal matrix. So, you have another 2 diagonals on the 2 sides of it. So, in the 3 dimensional you have another 2, so 7 total diagonals involved. So, it is possible to have several off diagonal or near diagonal terms, but the matrix is generally sparse. These types of matrices are called as sparse matrices, where the coefficients in many of the terms are zeros. So, you have essentially the diagonal coefficients which are non-zero, and you have some of the off diagonal coefficients which are non-zero, depending on I mean if it is a tridiagonal system then 3 diagonals, if it is a pentadiagonal system 5 diagonals, but these are not the only terms. So, you have majority of the terms which are away from the diagonal, these are zeros. So, the matrix is densely populated with zeros, and that these types of matrices are called as sparse matrices, and it is particularly important in computational fluid dynamics to understand how to handle these sparse matrices. Sparse matrices are actually very irritating, because if you are trying to represent the matrix as it is, then you are wasting a lot of storage space for storing zeros. We have seen that how cleverly that can be avoided for a tridiagonal matrix by using the tridiagonal matrix algorithm, by converting the storage from a 2 dimensional to a 1 dimensional storage. So, it is important to take care of that in the formulation of the solution procedure. Now, coming back to this effect of the neighbors. So, you have effect of the neighbors as summation of the mod of the neighboring terms divided by the grid point contribution, and that needs to be less than equal to 1 to satisfy the sufficient condition for convergence. Keeping this in view, Scarborough proposed a criterion which is called as Scarborough criterion for sufficient condition of convergence for the Gauss-Seidel method by taking clue from here, and let us state that. So, Scarborough criteria for sufficient condition for convergence, Scarborough criteria of sufficient condition for convergence in Gauss-Seidel method. It states that you must have summation of mod of A and B by mod of AP that is less than equal to 1 for all equations, and in addition one physically based criterion that is less than 1 for at least one equation. This is a very important consideration which we will try to discuss in more details. So, from the mathematical perspective that we have discussed so far, less than equal to 1 for all equations would have been good enough, because that means that if it is less than equal to 1 for all equations, that means for all rows considered together this is less than equal to 1. So, maximum row sum norm that is less than equal to 1. Now, why less than 1 for at least one equation? So, the criterion says that it is not good enough to satisfy this less than equal to 1, that inequality should be a strict inequality in a sense that it should be less than 1 for at least one of the equations that you are solving for. Thank you.